Hi, welcome to lesson 1 in the fluids unit. This lesson will be on the concept of pressure. In this lesson, we will define what pressure is, and we will talk about the factors that determine the pressure in a liquid, and then we will learn how to calculate the pressure in a liquid at various depths within that liquid. So to get things started, the first concept is, the main concept is pressure. And in physics, pressure is just defined as force divided by area, the amount of force applied over a given area. If we were to just use variables, the equation would be P equals F divided by A. Now the units of pressure, if you look at the equation, the units of force are newtons, and the units of area are meters squared. So the units of pressure are newtons per meter squared, but that actually gets shortened to something that we call a Pascal, or it's abbreviated a PA. So the units of pressure are in Pascal, or PA, as you'll see it written. Now 1 Pascal, just to give you some reference, is very small. It's about the pressure that you would experience if you were to place a dollar bill on your hand. So typically what happens is we will write pressure in kilopascal, which is equal to 1,000 pascals. Now what this all means, force divided by area, is this. If I draw a sketch over here, if we take two objects of the same weight, and they're shaped kind of like a trapezoid, this object right here, if I place it so that the small side is touching the ground, and then I turn it over so that the large area side is touching the ground, even though it's the same weight, it will exert a different pressure on the table. This is pressure 1, and that's going to be greater than pressure 2, even though the weight is the same. You could imagine taking a thumbtack and pushing the wide end on your hand, and it wouldn't hurt, or if you did the narrow pin part, it would really hurt a lot. So pressure is force divided by area. In a liquid in a container exerts forces on the walls and the bottom of the container. So at different parts in a liquid, there is pressure on every single wall when you put a liquid in a container. And there are three things that factor into this pressure. The first thing is the density of the liquid. The second thing is the depth that you're at. And the third thing is just gravity. So, for instance, if we're at two depths, let's say maybe point A and point B, one of the things that would matter is how deep you are. So at point A, there would be a lot less pressure acting on the walls or an object in that liquid than if you were at B. We can calculate this pressure in a liquid by using this equation. Pressure equals rho, which is a symbol that is used for density, times g, that's the acceleration due to gravity, typically 9.8 on Earth, times h being the depth or height of the liquid that you're dealing with. So let me just label these. This is density right here, and the depth is the h value, and gravity will be represented by the g value. And that's a way that we can calculate pressure within a liquid. I'd like to do an example of that with you in our example is the following. It says, calculate the water pressure at the base of the Hoover Dam. The depth of the water at the base of the dam is 220 meters. So to do this, we would use the pressure equation from the previous slide. Pressure equals rho, which is the density of water, times G times H. Now we actually know that G is 9.8 and that the height is 220 meters of water. We do need to know the density of water. The density of water is something that I'll give to you, and that's 1,000 kilograms per meter squared. So if we use these numbers that were given in the problem along with the equation, we can see that what the pressure at the base of the Hoover Dam is. This is if you were to scuba dive all the way down to the bottom. So it's 1,000 times 9.8 times 220, and this turns out to be a pretty big number. Calculated, you can try to calculate it on your own. That is 2,156,000, and the units are pascals. If you wanted to shorten that, you could write 2,156 kilopascals, and this would be our answer. Just to give you a comparison, because it's a pretty deep depth of water to go to. If you were to just calculate the pressure at the bottom of, let's say, the swimming pool here at the high school, which is 10 feet deep, so it's about 3 meters, you would still have the same type of liquid water, so we'd have the same density. And the swimming pool here is only about 3 meters deep, so if you dive down to the bottom of that, which you might have done at some point, you go to the bottom of the in-ground pool, the pressure is only 29,400 pascals, or 29.4 kilopascals. So the depth is really the key factor in terms of water pressure. Finally, one of the most important things about understanding pressure in fluids is to realize that the pressure in a liquid does not depend on the amount of the liquid. So the volume is not important. We can actually see that from the equation. But if we imagine two examples, first, I'm drawing a shallow lake, a large but shallow lake. Let's say maybe this is a huge lake. It covers a large area. It's only 5 meters deep. And we compare that to a lake maybe that's very deep, but it's not that big. So maybe something like this. So it's small, deep lake. Maybe it's 10 meters deep, so it's twice the depth. Even though the small lake has less water than a large lake, if you were to go to the bottom, pressure at point 1, if you were to go to the bottom of this one, pressure at point 2, this would be a greater pressure. Maybe I should write a large pressure. So let's write large pressure. And this is a smaller pressure. Even though you're in a lake that has a ton of water, because you're not very deep, you'll have a smaller pressure. But actually, if you were to go to the exact same depth, 5 meters, this would be the same pressure as the other lake. So depth is the most important factor when we're dealing with pressure in water, and that will be a pretty big and important factor later on in this chapter. Finally, I wanted to show you something called Pascal's basis, which shows us that the pressure does not depend on volume, only depth. And therefore, because of that, water will reach the same level in all the bases because the pressures are equal. You can see here we have a device that has some funny shaped objects. They have different volumes, but because the pressure at any given point is equal, the water stabilizes itself and always reaches an equal level. If you were to go to the bottom of this place, no matter where you are or what shape you're in, you're always going to experience the same pressure, the same depth. To summarize, the key points of this lesson are the following. Pressure is force times area, or force divided by area, and the units pascals. Liquid pressure depends on density and depth along with gravity. So we have the equation rho GH. And finally, liquid pressure does not depend on volume, but only the depth of the water. That's the most important thing. So I hope this lesson kind of gave you some insights into pressure. And to finish this lesson, this first lesson, you should go to the Google form and complete the quick summary questions.